Also, let me put some guidelines for the project, which we can talk about. Please, the headphone noise, turn off your... Let me see بس دي. Okay, so yesterday I sent you some guidelines for the project, and I will share the guidelines here with you. Okay. So the idea is that somebody asked me how many papers we need to have. So I put the lower limit because on the number of papers that you relevant papers يعني مش تحطوا لي يوتيوب lecture. You can have lectures that are online. You can look up tutorials that are online and add them. But I would like for you to use this experience to look up in Google Scholar for papers and publications that are relevant, good review papers, good publications that are relevant, and try to summarize them. Although we may not be able to understand the in-depth technical knowledge that is within them, but you can at least understand the technical contribution, the advancement, the challenges, the state of the art, the pros and cons of a given design. I'm sure we can read that out from those papers and their relevance. So let us have a minimum of 4 papers and a minimum of 6 pages excluding بده يكون في عندكم abstract, conclusion, or cover page. So these are the body of your discussion. Of course, this is the lower limit. Some of you may write more. So the grading will be based on the quality. يعني if someone gives me a good solid report with good knowledge embedded in it versus someone just copies the papers, there will be a Turnitin checking. So please show me that you put effort, show me that you have worked on the project. I'm not going to count 1, 2, 3, 4 references and then let me see the chat. Why you cannot hear me? 1 second. Okay. So Johnny, it's not about only comparing designs. It is more if you find something that is relevant or you know the material makes sense to you and it is informative about the topic. This is what matters. I'm giving the comparison as an example. So the idea is to figure out where the current research, what people are doing, what are their contributions in their area, and to summarize each contribution, even if it is separately. If you find that they are referring to each other, or if you find that, for example, one design, for example, for the approximate adder claims that this saves compared to the basic adder 20% versus someone else says this saves 30% power or energy, we need to focus what are the metrics that those people are using, where is the contribution heading, and how this is improving over the traditional way people were designing. So the idea is to have some critical evaluation or summary of the contributions of those papers. Is that clear? Okay, thank you. So هيدي بالنسبة للproject. هلا today we will continue. Jinan, what do you mean by samples? هلا for your project it's sample reports. I can try to dig out a decent report from last year and share it with you all. I don't want it to be scary for some and maybe discouraging for others. No, عمر هلا بكفي عن جنان. عمر, there are two parts for the project. انتوا حتكونوا teams of two. And you can alternate the simulation part يلي حطيت لكم النت list لإله بسمة is related with the HSPICE. It is basic. It's just trying to convey for you how we measure power, how we measure delay, and how as the chain increases, the number of stages increases, the delay of the path increases, and therefore my clock for the oscillator increases. هيدول أكتر part 2 related للبasics تاعونات الكورس. But to get you familiar to see how the signal as it propagates, it gets more delay, and as the number of stages increases and as VDD increases, بيتغير الكورنت, بتتغير الباور. Part 1, and this is intended to be not related to your project because simulating your project requires more time. The literature part of the project, اللي هو أول part, I assigned you different topics based on your preferences. And those different topics are to understand what is happening out there in the research world, to understand, and I think you might have picked يمكن approximate adders إذا ماني غلطانة. إذا غلطانة you may have picked another topic. There are some of these topics which have been very well researched out there, so حتلاقوا كتير resources عنهم بالليترشر على جوجل سكولر. إذا بتحطوا approximate adder design أو memristor logic, you can start with regular Google and then go to Google Scholar. And if anybody is finding difficulty finding papers on their topic, let me know. Okay. Is this okay? Thank you. Now for Jinan's question for the sample report, an ideal report would have a few papers, several papers, مش بس 4. الفونت فيكم تعملوها 11. إذا كل paper عملنا لها summary including some relevant figures منها بصفحة ونص، يعني إذا شلنا منها 3-4 references لنحطهم as our references towards the end. And if we pick few figures from it that are relevant to the discussion, and if we summarize it in one page, and later we have a concluding paragraph that says, well, based on what we saw, we think مثلا هيدي البيبر هي الموست recent, عطت مثلا better improvement than others. Even if you cannot comment, it is okay, but this would be a sample report. I will try to dig out a good sample report and send it to you over the weekend. Okay? حدا عنده بعد سؤال على البروجكت؟ Thank you. And then there will be towards the end of the semester, we will have a discussion session to make sure that you are familiar with what you wrote, that you somehow have an idea what is happening. Even if you don't know the underlying technology very well, it is okay, but I just want to make sure that you familiarized yourself with the report and that you were able to contribute to it. Okay? طيب. And you can split the tasks amongst each other بين simulation report, but make sure that all of you have contributed to both parts. This would be the ideal situation because it will be more helpful in the presentations and it will be a good learning experience when you can discuss things amongst each other. Okay? طيب هلا حنكفي lecture today. So let me click here. Okay, so last time we were talking about the wire capacitance and we talked about the interwire capacitance كان آخر example أخذناه. On this slide here, I'm just trying to give you a hint to that attofarad when he says AF هي 10 to the power minus 18, and you're familiar with the nano, pico, and femto from before. Okay, and then now they're trying to tell us, well, how is the industry, where is it heading in trying to reducing the capacitance on the chip. بما إنه الكاباسيتنس هو epsilon A على D، وبما إنه الإبسلون هي what matters for us، هي اللي بتعلي coefficient which shows up in those tables. They try to go for بالcapacitance low K dielectric. If you remember لما عملنا الترانزستور، للترانزستور الكرنت is proportional ل Cox. So بالcurrent بالترانزستور أنا I want to increase my Cox ليكبر الكرنت معه. Okay, so لهيك عملنا هاي K-way الhomework example. But for the interconnect or for routing the chip, we would like to drop epsilon. So we take the opposite way. We would like to go with low K dielectrics. So, and also, they may try even to put bubbles of air inside the interconnect, يعني inside the layers of dielectric field oxide الموجود بالشيب ليخففوا من حدة السيليكون دايوكسيد epsilon. هلا also they are moving to copper interconnect لأن it has low resistance. الR تاعيتها بتصغر. So إذا الR تاعيتها صغرت I can afford to have small cross sections ليقطع فيهم الكرنت. وإذا قطع الكرنت بهالسمول cross section بصير على القليلة عندي البارallel plate capacitance. إذا الW صغرت CPP كمان it can go lower. Okay, so نقلوا للcopper interconnect بدل الألمنيوم interconnect. هلا for the transistors themselves عملوا new technologies where they can reduce the diffusion capacitance أو reduce the junction capacitance تاع الترانزستور يلي هو كان موجود بالreverse bias diode يلي هي موجودة هون. Okay, so هاي كلها different ways of and efforts trying to reduce the capacitance to eventually اللي بهمنا نصغر الديلي لأنه لما الديلي دي الT delay بتصغر. This means that what I can do is I can have faster clocks, and faster clocks means I can do more processing. طبعا إلى تأثير على الباور بعدين بندرسه، بس إذا صرنا نشتغل at higher frequencies I can do more processing and therefore my processor is more efficient. So this shows us the link between the physical design, the interconnect, and eventually the system design where T clock the F clock will decrease يعني T clock will decrease. Okay, so the frequency عم تكبر. هلا one thing about the capacitance also why we are interested in designing for it هو coupling capacitance. Coupling effect can have two effects. It can either بس لشوف وين البن تاعوني. Okay. It can either affect my delay negatively, sometimes positively, and it can affect the signal integrity or the noise on the chip. اوكي هلا حنعطيكم فكرة بسيطة عن النويز بس حنحكي عن الديلي أكتر شوي وحنعطيكم homework problem عن الديلي. So أنا typically في عندي شيء بسموه victim net وفي عندنا شيء بسموه aggressor net. The victim it is really a silent signal that is not propagating ومفروض ما يكون عندي change of input لهون ولا هون ولا على الlatch. So the latch is supposed to give me no change in Q. What happens is exactly what happens when you have two racing cars. Okay, so if you have two racing cars or one standby car and one zooming car, the zooming car speed is going to affect this standby car and shake it. Okay, so in coupling إذا أنا عندي two wires هون two wires naturally في بيناتهم interwire capacitance C حنسميه coupling capacitance. If we have a signal that is changing here at this aggressor circuit, then the output of this inverter is going to change, it's going to go up. إذا هون عندي silent هيدي كأنها ideally small signal zero. Okay, so therefore what is going to happen, this capacitor from this side is seeing a delta V, okay? And we typically know that the capacitor will have a current C delta V by dt, okay? So the C dV by dt is going to create a current in this capacitor. And now this current, this transient current in this capacitor is going to flow in the capacitance that exists in this wire, between this wire and the ground. لأنه كل واير عنده its own capacitance كان silent أو لا. And the flow of this current is going to inject temporarily some charge onto this lower capacitor وحيغير state لهيدي النود. هالنويز اللي حنشوفه على هيدي النود هون. Okay, and we will later tell you why we see noise if this is silent. If I happen to have a clock that is coming at the same time, ما هي الكلوك حتضلها pulsing up and down up and down, I may by mistake latch it إذا كانت high enough and read a false signal at the output. Okay, so لهيك we try to be wary about the distance between two wires to make sure that they are not routed along each other or to shield the wires so that we do not cause by mistake latch faulty inputs and therefore do false evaluations on the chip. هلا what happens here, and this we are not responsible for any examination على قصة النويز. What really happens here, let us say that this inverter has a stable signal, which is 1. So the output here should be ideally 0. This is off, and this is on, okay? And the VDS for this inverter is 0. So هيدا الانverter is on, بس عنده VDS كتير صغيرة، هو باللينير. طيب لو كان إذا ال VDS is 0، إذا بنحط اللينير equation بيطلع عنا إنه ال current I هي 0 اللي قاطع بهيدا الترانزستور. Now if I get some noise and VDS becomes 0.1, I will become different from 0 لأنه الترانزستور جاهز و on. So it is going to try to discharge whatever builds up on this node. Okay, لهيك بنشوفها بتعلى شوي وبعدين بترجع تنزل. Okay, so this is what is happening. But what we want, the message that we want to take from this example is that CC is going to see a delta V, and this delta V will create some current, and this current will inject a current in other capacitors اللي هن قاعدين هون حيعمل لهم charging. But the circuit, because there is no noise at the input, will take care of itself and help discharge this noise. Now, depending how strong my circuit is and how strong the noise is, and when the timing happens, when the latching of the clock happens, I may or may not have a fault with my system. Okay? حدا عنده سؤال so far? Okay, so okay, 1 second, let me answer the question. Doctor, when we go to lower dimension, does the parallel plate capacitance decrease? When we scale, the width is shrinking. So the width is shrinking. The wires are getting longer because our chips are becoming bigger. The relative، ما هي كمان الترانزستور عم يصغر والكارنت تاعونه عم يكبر والكاباسيتنس of the transistor عم يصغر. So the relative capacitance يعني relative delay، ما نحن كل ما عم تنزل التكنولوجي عم نقدر نحسن الديلي. But the relative capacitance of the wire itself إذا صار longer حيكبر. The relative capacitance of the wire بالنسبة للكاباسيتنس تاعون الجيتس حيكون كبير. Okay, so the total capacitance كرelative quantity كتأثيرها على الديلي المتوقع عندي عم تكون أكبر لأنه إجمالي الوايرز عم بيصير أطول ولأنه الواير capacitance عم بيكون أكبر من الجيت capacitance. Okay, so as we scale, we are shrinking يمكن some capacitance, we are increasing some because we are making longer wires, but the importance of the interconnect capacitance is significant and we need to take it into account in my overall delay. وإلا مزبوط مثل ما عم بتقول لو كان عم يضل يكبر وأنا عم صغر الشيب وعم صغر الترانزستور كانت ما قدرت أنزل كبر الفريكونسي. Now, Mira, yes, the interwire capacitance becomes significant. So we have a lot of fringing capacitance. Sometimes to enhance the resistance, they might resort to keep the height not scaled too much. so that keeps the interwire capacitance له significance حنشوفها بعدين. The parallel plate من technology لتكنولوجي ممكن يصغر إذا بقي الواير length هو ذاته, but the relative effect compared to the gate capacitance and compared to the delay component حيكون كبير. Okay, so Muhyiddin is asking about the clock part. Okay, so Muhyiddin إذا نحن عنا if we have a latch, نحن على طول السيجنال, ما هي السيجنال بيكون عنا latch, بيكون عندي cloud of combinational logic and then another latch, لأنه that's how we divide our circuit لنقدر into parallel processing and into paths that feed each other such that the delay بين latch و latch بيساوي the time of the clock cycle, right? So what happens is that لهالباث okay حيجي عندي certain functional logic لنعتبره هو 1 inverter and 2 inverter وهيدي فايتة على Q. هون حيجي عندي clock. لنفترض إنه أنا I always latch at the falling edge of the clock. Okay. Now if it happens that this noise signal, let us say, reaches مثلا 3/4 VDD, okay, and let us think that if this happens right around the time of the falling edge of the clock, this latch is a circuit and it has transistors in it, and those transistors in it may turn on or off depending on the signal that they
Professor?
Yes, Omar.
We can't see the slides.
You cannot see the slide? Let me try it. 1 second. Is Zoom not sharing? Let me... I will unshare and share again. Maybe I don't know how to... Can you see it now, Omar?
Yes.
Okay. Before you were able to see it, Okay, so I was telling you that in the circuit we have typically a path between two latches with some logic. And let us say that this logic is the inverter that is feeding the latch. And every latch will be clocked by a clock. And we latch at the falling edge of the clock, okay? And now if the noise happens لفايت على الكيو to be large, okay? And it happens to happen around the same time when I am latching at the falling edge of the clock. What happens is that the transistors in the latch, هيدا might be turned on by this noise signal, another one might be turned on by the clock 5 يعني 5 bar اللي عم يقلبوا. So I will see something at the output يلي I may not have seen if I did not get by mistake. Sorry, let me go back. If I did not get by mistake this noisy signal here. Okay, يعني لو ما ثاقب النويز اجى مع falling edge of the clock ما كنا عملنا latching للفولس value. So there are many factors اللي هو ايمتى الكلوك حتجي وقديش كبر النويز وقديش السيركت كان absorb the noise. Is this clear? Is this clear? Okay. Okay, thank you محيدين. طيب هلا حنحكي عن الإفكت على الديلي. Okay, so if I have two aggressors, هيدا aggressor يعني هيدا عم يبعت لي signal طلعت له وهيدا عم يبعت لي signal طلعت له وهيدا is evaluating the opposite. عفوا هيدا عم يبعت لي signal هون طلعت له. Forget about this. And this is trying to go down. Okay, so خلينا نطلع what we have. بين every wire wire في عندي coupling capacitance. Now this is going up, this is going down. هيدي النود وهيدي النود. نرجع لقصة الميلر capacitance that says if I have a capacitor between two nodes 1 and 2 such that I know that the gain of V2 على V1 equal to K, then I can replace this by an effective capacitor, okay, at each one of these nodes. على هالجهة حيكون C into 1 minus K، okay، بينه وبين الجراوند، وبشيل الكاباسيتنس أنا من هون، ونفس الشيء هون ححط 1 minus 1K، هيدي بتصير C into 1 minus 1 over K. طيب. Let us erase some scratches and let us use the red color. أول شي خليني أمحي هون. Okay. طيب. So the first thing that we need to look at is what is the gain between the two nodes يلي هن الaggressor والvictim. So if we go to this node, هيدي is going up to VDD وهيدي is going down. So the gain is -1 لأنه عم باخد full range. اوكي عم يطلع اثنيناتهم بين 0 و 1 بس وحده opposite للثانيه. فماي K is -1. Okay. Therefore the effective capacitance will be C into 1 minus -1 يعني هو حيصير بيساوي 2 times C. Okay. So now let us see what happens to the circuit if I want to replace those things by their model or by their Miller equivalent. حنشيل هاي وهاي كمان. حنلاقي إنه if this is affecting me, what is going to happen, I will draw them in green. هيدا فيني شيله من هون إذا بدي أدرس هيدي النود. Okay. بس I have to replace it by a capacitor يلي هو 2 times إذا هاي كان C هيدا هو 2 times C. Okay. Now the same happens to this red one. كمان إذا هيدا كان طالع طلوع معاكس opposite to what this is supposed to happen, what is going to happen is that كمان هيدا it will go away and I'm going to replace it by a capacitance between this node and the ground. إذا هيدا can C, this will be 2 times C. But I already have my own capacitance, parallel place capacitance اللي هو C كمان كان 1 لنفترض وهيدا صار إذا هيدا 2 this is 2 إذا هيدا 3 this is 3. What happens is that now my total capacitance at my node, my total effective capacitance between my node and the ground has increased. يعني if someone is opposing me and the wire is close to me, what is going to happen is that it is going to increase my effective capacitance and therefore it is going to slow my signal. Okay.
Baby.
Amar, or who was that? Okay, can you silence your phone if you are not commenting on the course? Okay. So, and apologies if I told the wrong person. Okay, so what is going to happen now, if my capacitance increases, let us think why it increased, and let us logically think of the signals, what was happening to them. This was going up, so it was charging itself, okay, and any other capacitor يعني كمان كانت عم تكب current بهيدا الكاباسيتور. This was trying to go down, هيدا كان trying to go down, so it was trying to discharge itself to ground, okay, but this guy was injecting current onto it and it is charging itself. يعني إذا اعتبرنا هيدول shorted بدون الكاباسيتور, this is trying to go up and this is trying to pull it down. So what is happening is that this is opposing my signal and this is why we see an effectively increased capacitance at this node. Okay, so the idea is that the coupling capacitance إذا كان عندي aggressor, okay, gets multiplied by 2 and we see it between my node and the ground, okay? If the aggressor happens to be the same like me حيساعدني حيسرعني. It will make me faster. Okay? حدا عنده سؤال? Anybody has a question? طيب okay. Okay, thank you. Great. هلا we familiarized ourselves with the resistance, with the capacitance. Now we need to start to talk a little bit about the resistance, and then we will talk about them combined together. So where do we get resistance on the chip? We get resistance from the wire أكيد. We get resistance from the contacts. يعني أنا if I have multiple wire layers عم بنقل من layer للاyer لحد ما أوصل عند الترانزستور. Okay, if I'm going to metal 1, then to metal 2. Johnny, you were saying why it is slower. Okay, so I will go back. Yeah. Okay. Why it is slower for the, you're asking about my signal, why it becomes slower. Okay. So you understood that if this is going up, it's throwing a charge on its own capacitance, and it's throwing also charge through the coupling capacitor. It's like a partial connector. Anytime I have a slope, a current will flow through it. Okay? So logically speaking, if I'm trying to discharge things through this inverter here, but this inverter has its PMOS on, and it is trying to charge things up, it will throw a current. هتشارج هيدا والcoupling capacitor. Okay, so this will send me some current that is coming from VDD. يعني هيدا الcurrent من VDD through this PMOS is going through this and then coming back to my own capacitive node, right? Whereas I am trying to discharge, it's as if somebody is throwing water at me. Okay, it is as if this guy is throwing a charge and I'm trying to discharge. Now, if we look at this capacitor here as a coupling capacitor or as a Miller capacitor هيدا, okay, this signal here is going up and the signal here, we are trying to pull it down, okay? So the Miller capacitor is sitting between two nodes, واحدة منهم going up, واحدة منهم going down, and so the gain of those two, بما أنهم رايحين من 0 ل 1 أو 1 ل 0, dV by dt, if we assume they have the same slopes وكل شيء, الgain تاعهم هو -1 لأنه inverting. okay, صار أنا إذا بدي أطبق الميلر rule حأجي أقول I'm going to remove this capacitor, I will put a capacitor here and a capacitor here. هيدا هو الفاليو تاعونه إذا هيدي هي C، هيدول بين هيدول النودز والground. If this is C, this will be C into 1 minus 1 over K, and this will be C into 1 minus K. Okay, يعني this will become 2 times C and this will become 2 times C. Okay, now this capacitor is a هيدي node 1 وهيدي node 2 will be between node 1 and the ground. So فهيدا I'm gonna replace it by a capacitor here قيمته 2C وباي a capacitor here يلي قيمته كمان 2C. Okay, so now I don't only see my wiring capacitor but also my coupling capacitor affects me by twice of its amount because I have a gain of -1 لأنه the other person is opposing my signal وأنا كمان لأنه I'm opposing his signal I'm also affecting him by 2C. I'm also delaying him. هلا okay حيتغير slope حيخف شوي in both of us but we're seeing double the capacitance. Okay, thank you John. Okay, so now هلا we're gonna talk about the resistor. Where does the resistance come? It can come from the metal wire itself. يعني أنا إذا عندي wire مبعوث بلاير 3 في عنده resistance بلاير 3 ولاير 2 ولاير 1 وكمان من الكونتاكتس هيدا البيلر اللي عم بيوصل السيجنال من one layer على layer ما هو واير بالنهاية بس it is vertical so it has some resistance it doesn't have capacitance لأنه نازل vertical at least for now and then also الترانزستور itself ما هو عنده channel وعم يقطع فيها ال current so anything that has a current flowing in it as a material will have a resistor رح نقول له R on يعني أنا anytime I have a resistor a transistor two transistors مثلا in this case between this node and this node we will assume that I will represent them by two resistors إذا كانوا on اثنيناتهم حيكون عنا R on 1 و R on 2 okay if this is the ground here okay between this node and the ground okay great so we will start to see how we can tabulate things يعني نحن we can derive value for the R on and we will see how we derive it in the coming lectures but eventually we will say that those values will scale with my design يعني كل ما ال current كل ما ال W كبرت كل ما ال current كبر كل ما ال R on حتصغر resistor حيصغر حيصير faster and better delay okay طب here he's showing me a top view of the transistor في عندي poly gate so this is my G this is my source this is my drain وهيدول ال two pins تاعون الsource والdrain he's telling me if we want to be very systematic the current will come from the metal it will go through the source then through the gate then through a channel مش the gate sorry and then through the drain to the other metal wire and propagate so عندنا ال R on of the transistor عندي small source and drain resistance لأنه هن بالنهاية structure عم يقطع فيه current وعندي ال contact اللي طلع طلوع فيه ال current ليوصل على ال metal layer and then I have the wiring resistance. If I want to model my transistor as a resistor, really when VGS is greater than VT, I will have R on come in place وإلا إذا كان ال switch is off I have infinite resistor it's a pure open circuit to model this R on typically ما هو الترانزستور هو عبارة عن resistor between عبارة عن current source قاطع بين ال drain وال source okay and this current value is changing and therefore as VDS changes طبعا therefore we can model it really as a variable resistor اللي هو بين ال drain وال source طيب we cannot always afford to model it as a variable resistor because that's what simulators are for they take every time point we need to model it by some equivalent or effective resistance to model this effective resistance one way would be to rely on integration يعني اجي اقول هو الافريج او الانتجرال بين time 1 و time 2 لكل ال RDS values اللي انا قطعت فيهم يلي هن فعليا مقسومة على الدلتا تايم اذا بدي اعملها انتجرال اوكي يلي هو كل مرة على given time اذا بعرف ال VD وال ID بعرف شو هو resistance أو I can say well if my circuit is operating مثلا بعرف إنه VDS let us say that this is grounded and that this is VDD اللي على الجيت and let us say that I know that VDS the drain voltage is going down from VDD all the way to 0 so this is high and this is low and this is let us say is T1 okay and then we identify another T2 then I can find what is the value of R1 at T1 and I can find what is the value of R1 at T2 and I can take the average of it as R equivalent what I'm going to do now is I'm going حسبق شوي حاشرح لكم هيدي النقطة لأنه هاي مهمة لنا we will use it a lot in calculating the details وبنرجع بنشوفها بسلايدات تانيين but let me explain this a little bit more to you. So let me insert an empty slide now. Okay. And let us draw the transistor at a bigger scale. هيدا transistor, and let us assume that this is the gate and that instantaneously at this time the gate rose up to VDD and that the drain was initially high, so VD was high, هيدا drain, and then it has to start now to drop down to low. Okay, so حنحط هون التايم points يلي هن هيدي هي T1 and this is instantaneous, so دغري بعتبر إنه الgate is high. Okay, and then this is the drain, and the drain at time T1 كان high due to an initial condition حدا عمل له charging قبل لما كان my transistor is off, let us say through the PMOS. And then let us say that we want to calculate the delay. If we want to calculate the time it takes this transistor to pull down the drain to 0, really the delay is at 50% when the output reaches 50% its value. مش لما بيوصل على 0، لما بيوصل على VDD over 2. Okay, so we define, and let me make this larger, let me erase this. We define our time points T1 and T2 typically لما output بيوصل على 50% value. Okay, so فعليا my 50% point is here, and this is what defines my time point T2. If I want now to replace this transistor by an effective R-on, رح طلع له ال-R-on يلي لإله على 2 time points. أول وحدة هي T1 هلأ بنكتبها بالأزرق، وتاني وحدة هي T2. The first two things that I have to build when I want to know R-on is I really need to define what was its VDS at T1 and T2 and what was its current at T1 and T2. If I want to determine what is its current, then I need also to determine what is its VGS. صح؟ والريشيو ل VDS على IDS بيعطيني قديش هو ال R-on at time T1. وبعدين بنهون لكم إياها هيدي شوي, but let us now focus what are the values of the voltage to determine the current. At time point T1, VDS, VD was VDD. Okay, and S is always 0, so my VDS is VDD. At time T1, I always look at T1 plus. Okay, وبما إنه ال VGS عملت rising at T1 with an infinite slope, this means that VGS خلص قلبت ل VDD وضلت VDD أنا عم كفي الديلي اللي لإلي. So gate voltage أو input, we always assume that effective immediately it has switched, it flipped. بياخد next state تاعيتها. The one who keeps slowly going from the previous state to the next state who would drain. So drain at T1 was VDD. It did not yet have time to drop. And at the 50% point at T2, it reached to half its target value يلي هو VDD over 2. Okay, this is what really matters to us in many things that we will take next. هلا حنشوفهم شوي نرجع بالديلي بنشوفهم أكتر. Now that I have my two bias points, معي VDS معي VGS, if I know VDV set, if I know VT, I can find what IDS is. Okay, and therefore I can find the current for this point and I can find the current for this point. هيدي هي point 1 وهيدي هي point 2 وصار فينا نطلع resistance R1 وفينا نطلع resistance R2 لهيدا الترانزستور. اوكي, حدا عنده سؤال on this point؟ Okay, perfect. طيب, this is what really matters to us. Now, let me just check the 1 second. Now, let us go through the remaining slides. Okay. So now he's trying to tell me, well, if I want to go through the complex route of really integrating the value of the current, and let me assume that VDS is dropping from VDD to VDD over 2 VGS here VDD all the time. If I know that the transistor is in a given region, I can write its equation in that specific region، وأنا بصير بدي أعمل piecewise integration وبتصير صعبة وبيطلع معي هاي complex equation يلي هي هون. طيب بس أحسن لي أخذها كأفريج، طلع 2 are on values at the end points اللي هن T1 و T2 لأن it is easier for me for hand calculations. Okay, now in here he's saying, well, in some cases we can give you tables, and let us see somebody before decided to study this transistor which is transitioning between T1 and T2, and he changed VDD values, and he showed me a table of how R equivalent based on the averaging that we discussed before is going to drop as we increase VDD. And he's saying now, so we can give you a table for the NMOS and for the PMOS equivalently for some typical transitions. يعني مثلا VGS equal VDD و VDS عم تنزل من هالفاليو لهالفاليو، بس انتبهوا للشغلة إنه whole values حيتغيروا، هالaverages that you will calculate will change with VDD. And also those tables, which is very important for us to note because later we can use tables to build Elmore delay and other stuff which we'll discuss later, will scale with W by L. يعني احنا بنعرف كلمة W تكبر، I will decrease, and therefore increase عفوا، I will increase, and therefore R will decrease proportional. So if we tell you that this table R equivalent is for W by L equal to 1, and if we tell you that a certain device has 3 times the reference width, okay, then what you will need is you take this resistor value and you're going to divide it by 3. So بنصير نقول okay, then its resistance will be 1/3 the values that are listed in this table. Okay, so this is how we use tables. Tables are always built for W by L ratio equal 1, and then if a device has a certain W by L which is different by 1, you need to divide by that number so that we can scale down things accordingly. Okay. Okay, and I'm going to stop here for today. I will send you a report, a sample report over the weekend, and we will continue from Monday. I will see for the short quiz, since next week we have Friday, I think is a holiday. If I give you a short quiz, it will be about the basic table of the capacitance on Wednesday. برجع بعطيكم homework للweek that we have a holiday, and then this will allow us to take a more هيك بنكون درسنا الألمول delay، بصير فينا نعطيكم another embedded exercise maybe in the week after. Okay, بتكون الماتيريال matured more with you. Okay, thank you very much everybody, and I will send you follow-up emails. Have a good week and stay safe. Thank you. Bye. Bye.